Hi everyone, and welcome to our project, Molecular Dynamics on Quantum Computers. The aim of this project is to simulate the potential energy surface of a hydrogen molecule using a variational quantum eigensolver. This technique allows us to understand reaction rates better, giving scope for drug discovery. Here you can see what we're going to run through during this presentation. And here you can see the timeline of our 8 weeks at Praise. So, what is a VQE? A VQE is a hybrid algorithm that uses both quantum and classical techniques. In chemistry, it's applied to the Schrödinger equation to solve for the minimum eigenvalues of the Hamiltonian matrix. These minimum values correspond to the ground state energy of the system being modelled. In our situation, we use a general approach called the quasi-classical trajectories method, which combines a VQE with the equations of motion. This algorithm works by performing energy measurements using quantum simulators or real quantum hardware. These energy values are the sum of the measurements of the expectation values of each term that contributes to the Hamiltonian. The computed energy is then fine-tuned using a classical optimizer to obtain a new set of variational parameters. These are then used to prepare a new state on the simulator or hardware. This process repeats until convergence. The Born-Oppenheimer approximation. So the Born-Oppenheimer approximation is based on the assumption that the nuclei is much heavier mass than electrons. Therefore, the position of the nuclei is fixed as they do not feel repulsion or attraction forces as much. In turn, when representing the quantum mechanical energy of the system, the nuclear kinetic energy term can be neglected. However, the approximation still takes into account the changes in position of the nuclei to determine the electronic energy. Solving the Schrödinger equation for the electronic part leads to the rotational dynamics of the molecule, while solving the nuclear part leads to the vibration of the molecule. Together, this gives us a molecular roto-vibrational spectrum for the hydrogen molecule we are modelling, shown by the dynamic simulations in the next slides. So here we write the semi-classical model for the equations of motion, from which we set Runge-Kutta to solve the initial value problem. The system of differential equations, together with partial derivatives and the norm, are used to compute a distance. We implement the function corresponding to the right-hand side of the system by obtaining the derivative, part of which is done numerically.
Let's now take a look at the comparisons of the VQE curves. In our work, two different environments were compared for the calculation of the VQE curve, such as state vector simulator, which represent the ideal curve, and QASM simulator, as well as two different optimizers, such as Cobila and SLSQP, and two different variational forms for the ansatz, UCCSD and SU2. Here, we can verify the difference between the curves obtained with the two different environments, and thus compare the simulation with the ideal model. Also, the run was done on two different processors, such as Falcon and Canary, to which the IBM Q-Lima and IBM Q-Armonk devices correspond. Furthermore, we'll compare the curves obtained with the noise model referred to the processors mentioned, and with the noise mitigations technique. It was chosen to compare the two different optimizers for each of the variational forms for the run done on the real quantum computer. And these are the results for the IBM Q-Lima. Here we can see a direct comparison between the two different devices with respect to the ideal model. Ultimately, it was chosen to compare the various techniques with a single device, which is IBM Q-Armonk, choosing UCCSD as the variational form and ASP-SA as optimizer. Let's now pass to the molecular dynamics simulations. Runs were performed using the environment state vector simulator and with UCCSD as variational form and ASP-SA as optimizer, which proved useful for converging with less than 200 iterations. The comparison was made for different initial conditions, where both the vibration, in which both atoms possess zero momentum, and rotovibration, which include momentum of both atoms of the molecule, can be observed. Here, we can see the momentum only on one particle, thus enabling us to one atom be dragged a little by the other one. In conclusion, the comparisons show that UCCSD is better than SU2. The Kobyla optimizer is more efficient than SLSQP, but the ASP-SA optimizer is what best helps in convergence of results. The curve given by the noise mitigation technique follows very well the data obtained from the run on a real quantum computer. The simulations show a feasibility of combination of method of quasi-classical trajectories with VQE. Thank you for watching.